The ground you are standing on is moving away from almost everything else in the universe faster than it should be. Not because you are special, because of where you happen to live. Our galaxy, and everything in it, appears to be sitting inside a region where the universe forgot to put enough matter. A region of space nearly 2 billion light years across, thinned out and left emptier than the cosmos around it. And here is the part they leave out of the textbook. That emptiness may be quietly poisoning the single most important number in all of cosmology. The number we use to measure how fast reality itself is stretching apart. For years, two of the most careful measurements humans have ever made have refused to agree, and the thinness beneath your feet might be the reason why. If a fact like that makes the floor feel a little less solid, hit that like button and subscribe, because it only gets stranger from here. And tell me in the comments where in the world you're listening from and what time it is where you are right now. Pour something warm, turn the lights down. We're going down into the dark. Start with the version of the universe you were handed. The clean one. The one that fits on a single page of a textbook and feels almost too elegant to be wrong. In this picture, the cosmos is smooth. Zoom out far enough, past the planets, past the stars, past the swirling arms of individual galaxies, and the lumps blur away. Matter spreads out evenly, like cream stirred fully into coffee, until there are no streaks left. Just one uniform colour everywhere you look. This is the idea at the heart of modern cosmology. Physicists call it the cosmological principle, and it is exactly what it sounds like. When viewed on the largest scales, the universe looks the same to all observers, and it looks the same in all directions, meaning the average density of matter is about the same in all places, and the universe is fairly smooth on large scales. There is a quiet arrogance the principle strips away, and a strange comfort it gives back. It says there is no centre, no edge, no special address. Wherever you stand in the universe, whatever galaxy you were born in, the view is essentially the same. You are nobody special, and that is precisely why the math works. Isotropy and homogeneity are not just observational conveniences, they are deeply tied to the theoretical framework of general relativity, because Einstein's field equations describe how matter and energy influence space-time. But without simplifying assumptions, these equations are incredibly complex. Assume the universe is smooth and the impossible becomes solvable. The whole cosmos collapses into a handful of clean equations you could write on the back of a napkin. And it is not just a convenient guess. Approximate large-scale smoothness was confirmed by galaxy surveys, the 2DF Redshift survey and the Sloan Digital Sky survey. When astronomers built maps of hundreds of thousands of galaxies, they found the smoothness really does emerge. Not on small scales. On small scales, the universe is violently lumpy. The cosmological principle is spectacularly violated on small scales, because planets, stars, and galaxies should not exist in a perfectly homogeneous universe. But keep pulling back, and the lumps average out. The number fluctuations decrease with increasing scale, and drop below unity for a radius of roughly 8 units, indicating that on scales less than that, the universe is lumpy, and for scales greater, the universe becomes smooth. So here is the trusted picture, in one breath, a universe born in a single hot flash, expanding outward ever since. Every galaxy carried apart from every other galaxy like raisins baked into a rising loaf of bread. The dough is space itself, swelling in every direction, and the raisins don't push through the dough, they just drift apart because the dough between them grows. No raisin is at the centre. Every raisin sees all the others receding, and crucially, they all see the same rate of swelling, because the dough is the same everywhere. Hold on to that image of the even loaf, because two things are hiding inside it, and both will come back to hurt us. The first is the assumption that the dough rises at the same speed in every corner of the pan. The second is a small, uncomfortable question we are about to bury and then dig back up. What if our particular raisin isn't sitting in the dough at all? What if it's sitting in a bubble, a pocket where the dough is thin, where there's more air than bread? Sit with that, because we're going to need it. For now though, the picture holds. It's beautiful, it's simple, and for nearly a century it has worked well enough to build entire careers on. To understand why it worked and where the crack first appeared, we have to go back to the men who taught us the universe was moving at all. Rewind to the 1920s. Picture a cold observatory on a mountaintop in California, the great 100-inch telescope on Mount Wilson, and a tall, pipe-smoking astronomer named Edwin Hubble, spending his nights photographing faint smudges of light that no one was sure were even real. Some thought these spiral nebulae were clouds of gas inside our own Milky Way. Hubble proved they were something far more terrifying. Edwin Powell Hubble established in 1924 that many nebulae are stellar systems outside the Milky Way, when he discovered Cepheid variables in the Andromeda Nebula using the 100-inch telescope on Mount Wilson. In one stroke, the universe stopped being a single galaxy and became an ocean of them. Our entire home, everything humanity had ever known, shrank to a single island in an unimaginable sea. But the deeper shock came 5 years later. Hubble measured how fast these newly discovered galaxies were moving using the colour of their light. Light from an object rushing away gets stretched toward the red end of the spectrum, the same way a siren drops in pitch as an ambulance races past you and away down the street. In 1929, Edwin Hubble announced that almost all galaxies appeared to be moving away from us, and he found that the universe was expanding, with all of the galaxies moving away from each other, observed as a redshift of a galaxy's spectrum. And there was a pattern in it, clean and startling. Hubble's velocity-distance relationship, published in 1929, suggested that galaxies are moving away from one another, and not only are they moving away, but the more distant galaxies appear to be moving away faster than closer ones. Twice as far, twice as fast. 10 times as far, 10 times as fast. A perfectly straight line running through the data. That line had a slope, a single number describing how quickly the whole universe was flying apart. We call it the Hubble constant. It is, in a real sense, the expansion rate of everything. Now, here's a detail the textbooks tend to skip, and it matters for what's coming. Hubble was not really first, and he was not even sure what he'd found. 2 years earlier, a Belgian priest and physicist named Georges Lemaitre had already worked out that space should be expanding, straight from Einstein's equations, and had even estimated the rate. Some 5 years after Friedman, Georges Lemaitre also discovered dynamical solutions, and in the same publication he extracted the linear relationship between velocity and distance. Lemaitre saw the expanding universe on paper before Hubble photographed it in the sky. And Hubble himself was cagey. The cautious empiricist Hubble never claimed to have discovered the expansion of the universe, but only to have found an empirical law connecting the redshifts and the distances of the spirals. Even stranger, the man was measuring something he never directly saw. As a matter of fact, he and his collaborator Milton Humason never measured velocities directly. What they measured were the redshifts of these extragalactic nebulae. But in this crucial paper, Hubble considered these redshifts as representing real radial velocities. Read that again slowly. The entire foundation of modern cosmology rests on an interpretation. The colour shift is real. The idea that it means motion, that it can be trusted to tell you a clean, honest speed, is an assumption. A very good one, but an assumption. And assumptions, when they hide inside your most trusted instrument, are exactly the kind of thing that comes back for you later. Here's the other thing they got wrong, and it should give you pause about certainty itself. Hubble's first value for his own constant was catastrophically off. He measured roughly 500 kilometers per second per megaparsec. The number we accept today sits somewhere around 70, so his value was about 7 times too large, which made the whole universe look far too young. In fact, it made the cosmos appear younger than the rocks on Earth, which was a genuine crisis in its own right. The point isn't to mock the pioneers. The point is this: the single most important number in cosmology has been wrong before. Badly wrong. Held with total confidence by brilliant people. So when I tell you that today, with instruments 1,000 times more precise, we still cannot agree on that number, understand that this is not a footnote. It's a wound that has never closed. Because for decades after Hubble, the story looked like a triumph. Astronomers refined the number, argued over it, cut the uncertainty down and down. By the 2000s, 2 great methods had emerged, each pointing a different flashlight at the same dark question. Yet the moment those 2 flashlights disagreed, the comfortable picture began to come apart at the seams. The first way looks outward and backward to the oldest light there is. Just after the Big Bang, the entire universe was a glowing fog. When it finally cooled enough for that fog to clear, the light released in that instant went streaming off in every direction. And it's still arriving today, stretched into a faint microwave hum that fills the whole sky. We call it the cosmic microwave background. It is a baby photograph of the cosmos, taken when it was a few 100,000 years old. Read the patterns in that photograph carefully, feed them into the standard model, and you can predict exactly how fast the universe should be expanding now. That prediction comes out to about 67. Early universe estimates, inferred from cosmic microwave background anisotropies under the standard model, are consistent with values closer to 67, plus or minus about half a unit. The second way looks close to home, and it measures the expansion directly, the way Hubble did, only with breathtaking modern precision. You build what's called a distance ladder. You start by measuring the distance to certain types of stars within our galaxy, directly, through a method known as parallax. Then you use those stars to calibrate brighter beacons, and those to calibrate exploding stars visible across billions of light years, each rung of the ladder reaching a little further out. The main driver of the tension is a measurement by the team led by Adam Rees, who, because the supernova brightness is not known from first principles, built a distance ladder to calibrate the luminosity of 42 supernovae within 37 host galaxies. Do all that, measure the local expansion as directly as humanly possible, and you get about 73. Local determinations using Cepheid-calibrated supernovae yield values of about 73, plus or minus roughly 1 unit. 67 from the beginning of time, 73 from our own backyard. Those two numbers are not supposed to be different. They are two measurements of the same thing, taken from opposite ends of cosmic history, and in a healthy universe they would meet in the middle. They don't, and the gap between them refuses to close. For a while, everyone assumed this was a mistake. Somebody's ruler was warped, some subtle error was hiding in one of the methods, and once it was found, the two numbers would slide together and the whole thing would be forgotten. That is the reasonable hope. That is what a careful scientist expects. But the opposite happened. As the measurements got better, the gap didn't shrink, it sharpened. This discrepancy, dubbed the Hubble Tension, has now surpassed the 5 sigma threshold, making it one of the most statistically significant challenges to the standard cosmological model, and it remains unresolved despite substantial advances in measurement techniques and calibration precision. 5 sigma. In physics, that phrase has a specific and chilling weight. It's the threshold at which you're allowed to say you've discovered something. It means the odds of this being a random fluke are worse than 1 in a million. When two measurements of the same universe disagree at 5 sigma, one of two things has to be true. Either someone made a mistake so stubborn it has survived 30 years of the smartest people on Earth hunting for it, or the universe is not what we think it is. And people did hunt for the mistake. They tore the distance ladder apart rung by rung. They wondered whether the exploding stars were being subtly miscounted, whether crowded starfields were fooling the cameras. So they brought in the most powerful eye ever launched, the James Webb Space Telescope, and remeasured everything with fresh technology. Hoping to relieve the tension, some scientists speculated that unseen errors in the measurement may grow and become visible as we look deeper into the universe. In particular, that stellar crowding could affect brightness measurements. When you are trying to solve one of the biggest conundrums in cosmology, you should triple-check your homework. The homework checked out. All galaxies observed by Webb, together with their supernovae, yielded a Hubble constant of about 72.6, nearly identical to the value found by Hubble for the very same galaxies. The new telescope agreed with the old one. The high number held. Despite the smaller dataset, the team achieved impressive precision, showing differences between measurements of under 2%, far smaller than the roughly 8 to 9% size of the Hubble tension discrepancy. Whatever is wrong, it isn't a smudge on the lens. Adam Rees, who won a Nobel Prize for related work, has said it plainly. According to Nobel laureate Adam Rees, our measurements keep getting more precise, and the tension doesn't go away. So sit with where that leaves us. Two of the most careful measurements in the history of science, both refined for decades, both cross-checked by rival instruments, both standing at better than 5 sigma, and they will not agree. The universe is handing us two different answers to the same question, and it is not blinking. Something in our picture of reality is broken. The only question left is which piece. This is where the ground beneath us starts to feel less like solid rock and more like a thin crust over something hollow. Because there's a possibility that doesn't require breaking the laws of physics at all. A possibility that says both numbers might be right, and the problem is simply where we happen to be standing. To see it, we have to stop trusting the map and start counting the galaxies around us, one by one. The counting had been going on quietly for decades, and almost nobody outside a small circle of astronomers noticed what it was showing. The idea was simple. If the universe is smooth on large scales, then no matter which direction you look, and no matter how far, the galaxies should thin out in a predictable, uniform way. Count them near, count them far, and the number should climb smoothly, the way the crowd in a stadium looks equally dense whether you glance at the seats beside you or the seats across the field. Except that when astronomers actually did the counting around us, the seats nearby looked strangely empty. The trouble first showed up in the infrared, and there's a good reason for that. Visible light is easily fooled. Bright young stars flare, dust hides things, and the eye is drawn to fireworks rather than substance. But infrared light traces something more honest. Near-infrared photometry accurately traces the stellar mass, and is therefore a good proxy for the underlying matter distribution. It follows the old, quiet, heavy stars, the ones that actually add up to most of a galaxy's weight. So if you want to know how much stuff is really out there, you count in the infrared. And the infrared kept whispering the same uncomfortable answer. Galaxy counts in the near-infrared revealed that the local universe is significantly underdense on a scale of 2 to 300 megaparsecs around us. The hints go back a long way, further than most people realise. Back in 2012, one astronomer found a significant lack of galaxies within a sphere of radius 160 million light-years centred on our local group, reporting that the average mass density is a factor of 3 to 4 lower than predicted by the standard model. 3 to 4 times too empty in our own neighbourhood. That should have been a scandal. Instead, it was a curiosity, filed away, because a single measurement can always be wrong, and because the smooth universe was too beautiful to give up over one strange count. Then, in 2013, 3 astronomers put their names to the emptiness and made it impossible to ignore. Ryan Keenan, Amy Barger and Lennox Cowie ran the most careful infrared sensors yet. The region is named after astronomers Ryan Keenan, Amy Barger and Lennox Cowie, who studied it in 2013. They didn't just glance at the sky, they built a catalogue of tens of thousands of galaxies, measured how the density of matter changed as they looked outward, and found something that shouldn't exist in a smooth cosmos. In 2013, Keenan, Barger and Cowie discovered that the local universe is underdense on a much larger scale by counting galaxies at near-infrared wavelengths, finding evidence for an incredibly huge region of low density, with a density about 2 times lower than the cosmic mean, and with a radius of about 1 billion light-years. They gave it a name that has stuck, the KBC Void, their 3 initials, though astronomers also call it, more plainly and more ominously, the local hole. And I want to be careful with that word, void, right from the start, because it misleads. This is not a place where nothing exists. It contains the Milky Way, our whole local group, and a great many galaxies besides. The stars still burn, the light still travels. There is simply less of everything here than the smooth universe demands. Call it a hole if you like, but remember it is a hole full of galaxies, just too few of them. Its scale is where the story stops being an academic quibble and starts crawling under your skin. The underdensity is proposed to be roughly spherical, approximately 2 billion light-years in diameter. Try to hold that number in your head, and you can't. 2 billion light-years. Light, the fastest thing there is, moving at nearly 200,000 miles every second, would need 2 billion years just to cross it. When that light set out from the far wall of the region, there were no humans, no primates, barely any complex animals on Earth at all. The emptiness we apparently live inside is older and wider than the entire story of life on this planet, and we are not near the edge of it, tucked safely in some dense corner. As with other such regions, it is not completely empty. It contains the Milky Way, the local group, and the larger part of the Laniakea supercluster, with the Milky Way within a few 100 million light-years of the region's centre. Near the centre of a thinned-out cavity nearly 2 billion light-years across. This is the detail that quietly rewrites your address. You are not floating in the average universe. You are sitting close to the middle of a vast, thinned-out region, and everything you have ever seen through a telescope, you have seen from inside it. Now, one careful word again, because honesty is the whole point. Measurements of just how empty it is still vary a great deal. Like the Boötes void, the KBC region is not a true void, but an area of underdensity, with measurements varying from around 15 to 50% less dense than the surrounding regions. Roughly a fifth of the matter that should be here is somewhere else. And that missing fifth, it turns out, may be enough to fake a crisis. Because when you sit inside such a region, the whole universe starts lying to you about how fast it's moving. To feel why, forget space for a moment and think about water. Imagine you're floating in the exact centre of a wide, shallow pond that someone has just begun to drain from all sides at once. You're not swimming, you're just drifting, but the water beneath you is being pulled outward in every direction, toward the edges where it can escape. And because you're near the middle, everything around you starts sliding away from you at once. The pond doesn't have to push you, the drain does the work. To you, sitting still in the centre, it looks like the whole pond is fleeing outward, faster and faster the farther out you look. A cosmic underdensity does the same thing to space, and the mechanism is gravity. Such a region has less matter than average, which means it has less gravity than average. And the denser regions surrounding it, the walls of the hole, packed with extra galaxies, pull on everything inside. Gravity in these regions is slightly weaker due to the reduced mass. Matter inside gets tugged, slowly and steadily, toward those denser outer walls. It drains outward. A potential solution is that our galaxy is close to the centre of a large, local, underdense region, which would cause matter to be pulled by gravity toward the higher density exterior, leading to the region becoming emptier with time. As it empties out, the velocity of objects away from us would be larger than if the region were not there. This therefore gives the appearance of a faster local expansion rate. There's the trap, and it is elegant and horrible. You measure the expansion rate by watching how fast nearby galaxies recede from you. But if you're sitting in a draining pond, those galaxies aren't just receding because the universe is expanding. They're also sliding away because they're being pulled toward the walls of your hole. You can't separate the two. The extra outward drift gets folded into your measurement, and the expansion looks faster than it really is. Not because space is stretching faster here, because you're sitting in the middle of the drain. Galaxies inside such a region experience a gravitational pull from outside it, which yields a larger local value for the Hubble constant. And the part that lands like cold water down the back of your neck is the size of the effect. When you run the numbers on the actual KBC region, the size of the fakery comes out almost exactly right. In one recent study, it was calculated that the KBC region could cause a local Hubble constant about 11% higher than the global average. That's just the amount needed to bring local and distant measurements into harmony. 11%, that's the gap. That's the entire Hubble Tension, the crisis that has haunted cosmology for over a decade, the thing that made people whisper about new physics and broken models. And a thinning of space, centered right where we happen to live, could produce exactly that much error, all on its own, without changing a single law of physics. That should stop you cold, because it means the crisis might not be in the universe at all, it might be in our zip code. The two clocks we started with might both be telling the truth. The early universe clock reads the real, honest expansion rate of the cosmos as a whole. The local clock reads a rate contaminated by our own location, inflated by the drain we're sitting in. We built our most fundamental measurement of reality from inside a distorting bubble, and never knew the bubble was there. Which raises a question so simple it's almost childish, and so dangerous it could break the whole standard model. Is a region this empty even allowed to exist? Because if it isn't, we have not solved the tension. We've traded one impossible thing for another. This is the fork in the road, and both paths lead somewhere frightening. Remember the smooth universe, the even loaf, the cosmological principle that says on large scales everything averages out. An underdensity 2 billion light-years wide is not a small dent in that picture, it is a crater. And the Standard Model has a very specific, very uncomfortable opinion about craters that size. It says they shouldn't be there. The Standard Model assumes that on scales larger than a few 100 million light-years, the universe is smooth and uniform, which makes a region as large as the KBC a serious challenge. How serious? Put a number on the improbability and it becomes almost absurd. According to one calculation within standard structure formation models, for such a large underdensity to form, early density fluctuations would have to be extremely rare, about a 1 in a billion event. Yet the data suggest that the KBC region is real. And if it is, it likely means that the Standard Model doesn't describe large-scale cosmic structure as well as once thought. 1 in a billion. That is that model's estimate of the odds that a region this deep and this wide could exist by chance. And when you actually run the full simulations of how structure grows in our universe, the tension gets even worse, not better. The KBC region is a local underdensity, with an observed density contrast of about 46% out to 300 megaparsecs. If mass is conserved, such an underdensity could explain the Hubble tension. However, simulations show that the KBC region itself causes more than 6 sigma tension with standard cosmology. Read what that quietly concedes. The region was proposed to solve one crisis, and in solving it, it detonates a second. If the emptiness is real and as deep as the galaxy counts suggest, then the Standard Model is contradicted not once, but twice. Once by the mismatched clocks, and once by the sheer existence of the hole itself. Put those together and the numbers become brutal. Combined with the Hubble tension, the Standard Model is ruled out at more than 7 sigma confidence. So this is not a comfortable escape hatch, this is a trap with 2 jaws. Either the region is real, which means it can rescue the expansion measurements, but only by breaking the smoothness that the whole model is built on. Or it isn't as deep as claimed, in which case the smooth model survives, but the Hubble tension roars back with nothing to explain it, pointing straight at some genuinely new and unknown physics. There is no version of this where everyone gets to keep their comfortable assumptions. Something we were sure of is wrong. We just get to pick which. I want to be honest with you, because the fear only works if it survives fact-checking. Not everyone agrees the region is even there. This is a live, unresolved argument between serious people, right now, in the pages of peer-reviewed journals. It is debated whether the existence of the KBC region is consistent with the Standard Model. While one group says underdensities as large as this are inconsistent with it, another group argues that they are. One camp counts galaxies in the infrared and sees an undeniable hole. Another camp looks at exploding stars and sees no hole at all. That second camp landed a heavy blow in 2019. A team including Adam Rees himself, the same Nobel laureate at the centre of the tension, took the largest catalogue of supernova distances ever assembled and asked a direct question. If we're sitting in an underdense region, the extra outward drift should leave a fingerprint in how these exploding stars recede from us. Is the fingerprint there? Their answer was a flat no. They concluded that the distance redshift relation of their sample is inconsistent with the large local underdensity proposed by Keenan and colleagues at 5.3 sigma, and that of another study at 4.5 sigma. The supernovae, they argued, simply do not show the outflow a region that deep would cause. Given that the uncertainty in the distance ladder value is about 2%, they said, this does not affect the Hubble tension. For a while, that looked like the end of the story. Case closed, back to the drawing board. But science is rarely that tidy, and the defenders came back with a sharp objection of their own. They pointed out that the supernova study had baked in an assumption about how such a region behaves. An assumption, they say, was simply wrong. The local void scenario was challenged using the distance redshift relation of supernovae. However, those authors assumed that a local underdensity would have essentially no effect on redshift beyond a certain nearby distance, which is not the case in the more detailed models. In other words, the test that supposedly ruled the region out may have been testing the wrong shape of region. And there's a subtler knife hidden in that same critique. The exploding stars we lean on so heavily aren't perfect rulers. It may also be relevant that supernovae are not standard candles, but merely standardizable. They have to be corrected, tuned, adjusted, and those corrections can quietly smuggle in assumptions about the very cosmology you're trying to test. Which side of that exchange has the stronger case is itself still open. The supernova test did not close the question. It reopened it. So the disagreement is real, and it is not settled. But notice which way the newest evidence has been leaning, because in the last 2 years, the region has stopped being just a story told by galaxy counts and started showing up in places nobody expected. The strangest confirmation came from motion. If we really are sitting in a draining region, then the galaxies around us shouldn't just be receding, they should be flowing, coherently, in bulk, like a slow tide pulled toward the denser walls. And in 2023, a team measuring exactly this kind of large-scale motion found something that made cosmologists sit up. Galaxies in the Cosmic Flows 4 catalogue have significantly faster bulk flows than expected in the standard model, on scales of 100 to 250 megaparsecs. The tide was moving too fast. Far too fast. This bulk flow has less than 1 chance in 3,000 of occurring in the standard cosmological model. But it is precisely what you'd expect if a giant underdensity were draining out beneath us. And then came the sound of the Big Bang. In July of 2025, at the Royal Astronomical Society's national meeting, an astrophysicist named Indranil Banik presented a result that turned the region from a fringe idea into something much harder to dismiss. He'd gone looking for it in the most ancient ruler we possess, the faint pressure waves frozen into the early universe. Just after the Big Bang, sound waves rippled through the hot cosmic fog, and when the fog cleared, those ripples froze in place, leaving a preferred distance stamped between galaxies across the whole sky. These sound waves travelled for only a short while before becoming frozen in place once the universe cooled enough for neutral atoms to form. They act as a standard ruler, whose angular size we can use to chart the cosmic expansion history. A local underdensity, by tugging on the light passing through it, should subtly warp that ruler in a measurable way. Now, one crucial caveat before the number lands, because it changes how you should hear it. Banik's model leans on ideas that themselves challenge the standard picture, versions of physics where gravity is stronger than we think, or structure grows faster than it should. Because in ordinary physics, a region this deep simply can't form fast enough. So the result is not a clean, model-independent confirmation. It is a statement about how well one particular framework fits the data. With that firmly in mind, hear the number. By considering all available baryon acoustic oscillation measurements over the last 20 years, they showed that within that framework, a model with the region is about 100 million times more likely than a model without it, tuned to fit the early universe observations. 100 million times more likely. It is not the language of a fringe hypothesis, though it is still the language of a contested one. The sound of the beginning of time, read through this lens, seems to be telling us we live inside a hole. Banik is careful, and so should we be. The escape from one crisis still runs through the wreckage of another. But listen to how Banik himself frames where the tension actually lives. The Hubble tension is largely a local phenomenon, with little evidence that the expansion rate disagrees with expectations in the standard cosmology further back in time. So a local solution, like a local underdensity, is a promising way to go about solving the problem. Sit with the full weight of what that means, because we've climbed a long way down now. If the region is real, then the crisis was never in the universe. It was in us, in our position, in the accident of where our galaxy drifted to over 13 billion years. Every measurement of cosmic expansion we've ever made from close to home, every value on every chart, was taken from inside a distorting lens we didn't know we were looking through. We thought we were reading the universe. We were reading our own address and mistaking it for the cosmos. That opens a door I want to leave you standing in front of, rather than walk you all the way through. Because if our location can secretly warp the one number we trusted most, the expansion rate of everything, then the question is no longer just about the Hubble constant, The question becomes, how much else of our cosmic map was drawn from this same distorted vantage point? The size of things, the age of things, the behaviour of that mysterious dark energy we invented to explain an acceleration we measured from right here in the middle of the drain. We built a picture of all of reality while sitting inside a hole and called it the universe. The unsettling part isn't just that we might be wrong about the expansion rate, it's what our location might still be hiding in every other number we ever trusted, waiting quietly in the emptiness for someone to finally look down. That door opens not as a new thought, but as the answer to your final question. What else our location hides is beginning to surface, and it's surfacing in the raw numbers themselves. Look wherever you like across the sky. Point the telescopes north into the constellations you learned as a child. Point them south into skies humans have only mapped in the last century. The counts keep returning the same quiet confession. The region surrounding us holds roughly a fifth fewer galaxies than the statistical models say it should. And that gap has a cruel habit. It widens as the telescopes get sharper. The better we see, the emptier our neighbourhood looks. You'd expect a claim like that to rest on one shaky survey, easily dismissed. It doesn't. It comes from the deepest all-sky maps ever built. The infrared surveys that see straight through the curtains of dust that hide ordinary starlight. The 2-micron all-sky survey traced the edges of the thinness in the heat of old stars. The Sloan Digital Sky Survey, which catalogued hundreds of millions of objects across a third of the sky, mapped the deficit in exquisite detail. Different instruments, different wavelengths, different teams, different decades, all of them arriving at the same reluctant conclusion. There is less here than there should be. Names are strange things. We give them to hurricanes and to craters and to the vast thin places in space. And the moment a terrible thing has a name, it stops being an abstraction and becomes a place, a location on a map, somewhere you can be. And this one, you are. Not near its edge, where you might hope to peer out through the wall into the denser universe beyond. Suspended close to the middle of a region so sparse that the ordinary density of the cosmos simply fails to assemble itself around you. Try to feel the geometry of that, because it produces a very particular kind of vertigo. In every direction you look, the thinness runs outward for hundreds of millions of light years before you reach the crowded walls. Up, down, left, right, forward, back. There is no near shore. The emptiness surrounds you on all sides at a depth the human mind was never built to hold. It is the address where your galaxy happens to float, arrived at by nothing more than the slow drift of 13 billion years. And the scale of it is the kind of thing that most people go their whole lives without ever having to feel. Here's why this quietly rewrites what you thought you knew about the expanding universe. Picture a crowd standing in an open plaza on a summer evening, evenly spread, everyone drifting apart from their neighbours at the same lazy pace. Now imagine half that crowd steps away, sideways, into an adjoining hall that is far less packed. The people left in the plaza watch the remaining crowd thin out faster than it truly is, because part of what they're seeing isn't the plaza spreading, it's the fact of their own emptying location. They mistake the geometry of where they're standing for a property of the crowd itself. The region does the same to us, and the mechanism is gravity. Fewer galaxies between here and the distant universe means less matter tugging back on everything, less gravitational drag to slow the drift apart. The light reaching us from far away carries a record of expansion that looks steeper than it would from a normally dense stretch of space. This is where the horror stops being about one stubborn number and starts spreading. Because when we measured the acceleration of the universe, the discovery that space isn't just expanding but speeding up, part of what we saw might have been the edge effect of our own local emptiness. Now, I need to hand you the consensus first, because that is where honesty demands we begin. Most cosmologists still consider dark energy real and separate from any effect of our location, backed by several independent lines of evidence stretching well beyond our local patch. Dark energy won a Nobel Prize and became the largest single ingredient in the entire universe, roughly 70% of everything that exists. That is the mainstream, and it is well supported. But there is a minority view, argued by serious researchers in real journals, that if the region is real and deep enough, part of that measured acceleration might not be a pure force at all. Part of it might be our location, confessing itself as a flaw in the measurement. That is the speculative edge, not the centre. Yet the fact that this question now has to be argued about at all, that people who do this for a living have to ask how much of our foundational picture is contaminated by our address, that alone should unsettle you. Nobody can yet answer it cleanly. Which is exactly when the first real counter-argument walks in, and it is not a weak one. Standard cosmology, the framework that has held since the days of Hubble and Lemaitre, says a region this deep and this wide should almost never form. The mathematics of how structure grows predicts a universe that knits itself into an even weave over the largest scales, denser threads and sparser gaps balancing out, so that above a few 100 million light-years, everything smooths toward the same average. A hole the size of the KBC region tears that prediction. In the standard picture, it simply should not be there. So we arrive back at the trap with two jaws. But now we can see how the researchers themselves are splitting over it, and the split is real. One faction says the region is genuine but not impossible. In their reading, our understanding of how structures assemble is merely incomplete, and underdensities this large are more common than the simplest models allow. That would be a humbling correction to the theory, a bruise to our pride, but not a revolution. The furniture stays in the room. We just admit we miscounted it. The other faction takes the darker view. They argue the emptiness may be even more real, even deeper than the cautious estimates suggest, and that its very existence points to something structurally broken in the model, a crack that runs beneath the whole foundation rather than through a single prediction. Between those two camps sits a chasm, and everyone working on this problem knows perfectly well which edge of it they're standing on. That is not the language of settled science. That is the language of a discipline holding its breath. Follow the darker path all the way down and ask what it actually means if the deep region is allowed to exist. If we truly sit inside a genuine underdensity, then every distant measurement we make gets bent by our local thinness, and the consequence of that is far stranger than a single wrong number. It means the universe does not expand at one clean, universal rate at all. It expands differently depending on where you stand and which way you look. The one thing the cosmological principle promised us, that no place is special, that the view is the same everywhere, quietly dies. Our view is not the average view. It is the view from the bottom of a hole. Once that's true, watch what dissolves with it. The age of the universe, calculated from an expansion rate we may have measured wrong. The density of matter weighed against a background we may be misreading. The strength of dark energy, inferred from an acceleration our location may be faking. The predicted fate of the cosmos itself, whether it drifts apart forever into cold and dark. All of it inferred from inside the distortion. These aren't independent pillars. They lean on one another, and they all lean at the bottom on the assumption that our vantage point is ordinary. Kick that assumption away, and the numbers don't just wobble. They turn into local artifacts, portraits of the universe as seen through the accident of our address, painted in the warped glass of a funhouse mirror and hung on the wall with the word reality written underneath. Don't let anyone tell you the possible distortion is small. If the region is real and deep enough, the true uniform expansion rate of the whole universe could be meaningfully lower than what we measure from here. The acceleration we detected could be gentler than we think, or restructured into something we haven't correctly named. The confident predictions about how everything ends, the certainty about how it all began. Each of those becomes contingent on our not being wrong about where we sit. And that contingency is no longer a philosopher's daydream. It's a live variable in real equations, being fought over in real papers, right now. There's a particular cruelty in this that's worth naming slowly. We have a single vantage, and it is the only vantage we will ever possess. There is no second chair in the theatre, no neutral balcony we can climb to for a corrected view. Every eye humanity has ever pointed at the sky has looked out from the same distorting bubble, and no future instrument changes that, because the instrument would sit here too. We describe the whole play from one warped seat, unable to walk to the back of the room and check whether the stage looks different from there. If the seat is bent, we cannot, from the inside, measure by how much. That is not a gap we can simply observe our way out of. It's built into being here. And yet the region refuses to settle into either camp. It hangs, right now, at the very border of being allowed to exist. Deep enough to rescue the mismatched clocks, but so deep it threatens the smoothness the whole model needs. Rare enough that the standard picture calls it nearly a miracle, yet real enough that the ancient sound waves of the Big Bang seem to whisper its presence when read through the right lens. It sits in the doorway between two universes. One where we were simply unlucky in our address, and one where our deepest theory of everything must be broken open and rebuilt from the ground. Which of those two universes we live in is not a matter of opinion. It's a matter of measurement, and the measurements are coming. New surveys are already fanning out across the sky, mapping tens of millions of galaxies, tracing the exact shape and depth of the emptiness around us with a precision the pioneers could never have dreamed of. Within a handful of years, the data will force the fork closed. Either the region will harden into fact, and we'll have to swallow that we've been reading the cosmos through distorting glass, or it will dissolve under scrutiny, and the Hubble tension will come roaring back, with nothing left to blame but genuinely new physics, some unknown ingredient hiding in the dark. There is no third door where everything we believed stays intact, so the emptiness waits, patient, enormous and centered, as far as we can tell, almost exactly on us. And the deepest unease isn't the whole itself. It's what the whole implies about every other number we've ever trusted, and how little standing we have to check them. We came out here with instruments and confidence, and we measured the universe. What we may have measured instead was the shape of the room we were standing in the whole time. The walls are still out there in the dark, hundreds of millions of light years away, and we are only now beginning to reach toward them, feeling for the edges of a space we never knew we were inside. The walls don't have to be uniform to trap us. That's the thought that arrives last, and it's the coldest one. Because everything we've said so far quietly assumed the emptiness is smooth, a clean spherical bubble with us near the middle. But there's no law that says a thin place in space has to be tidy. If it deepens in patches, if it runs thin along some directions and thick along others, then expansion appears to pull faster here and slower there. And the moment that's true, the very idea of a single universal rate stops meaning anything at all. What we called the expansion of the universe fractures into a patchwork of regional readings, each measured at its own apparent pace, and our tidy single number becomes a fiction we told ourselves from one spot. This is what it actually costs to admit that smoothness might be wrong here. That one assumption sits buried so deep in every equation that almost nobody thinks to question it. It's not a variable you solve for, it's the paper the math is written on. Pull it out, and our measurements of expansion may not describe the whole cosmos at all. They may describe only the warped local patch we happen to inhabit, misread as the destiny of everything. The way you might soak one edge of a page and watch the ink run unevenly, faster along some fibres, slower across others, following a grain in the paper you never noticed was there. If that's the shape of things, then even our picture of the far future becomes something we measured from the wrong seat. The confident story about how the expansion carries every distant galaxy beyond reach until the sky empties of everything but our own local island of stars rests on the same numbers, gathered from the same distorted vantage. Some cosmologists call that far endpoint the era of isolation. But whether it arrives on the schedule we predict, or gentler, or not in the shape we drew at all, depends on whether the rate we measured from inside the hole was ever the true rate to begin with. Even the ending we imagined for the universe is a reading taken from the bottom of the drain. Read that slowly, because it turns the whole story back on us like a mirror. We are the ones doing the measuring in the narrow window of cosmic history when the evidence is still here to read, when the light of the beginning still arrives, when the walls of the emptiness are still close enough to feel for. Whatever the true shape of our location, we are the observers who got to look while there was still something to see, and to notice, with a chill, that the seat we look from might be bent. And yet, all of this remains unproven. I won't pretend otherwise, because the honesty is what makes it bite. The maps are uncertain. The surveys still contradict each other in whispers rather than shouts. Dark energy might be a rock-steady constant, or it might be slowly evolving, or it might turn out to be partly an illusion born from where and how we measured. The James Webb Space Telescope is out there right now, reading the oldest light, trying to catch the expansion's earliest behaviour before our local distortions could touch it. Radio dishes, X-ray eyes, gravitational wave detectors, each one circling the same central doubt from a different angle. Does the model hold everywhere, or does it break here, under our feet? Every new measurement does one of two things. It confirms the crisis, or it generates a stranger one. With each contradiction, the spiral tightens rather than loosens. That's the part that unsettles the people doing this work. They keep expecting the numbers to relax, to slide together, to let everyone go home. Instead, the numbers keep hardening, keep sharpening, keep insisting that something we were sure of is simply not true. The tension has outlived every attempt to kill it. Now step all the way back and notice something about the clock we're reading all of this on. Everything I've described tonight, the tension, the emptiness, the drift of the local group, the sound of the early cosmos frozen into the sky, all of it has been visible to us for only a few human lifetimes. We have looked outward with instruments precise enough to matter for perhaps a century and a half. 150 years to build the tools. 150 years to even notice that the universe is not the thing we said it was. Set that against the age of the cosmos, and it's less than a single heartbeat in a life that spans decades. We are newborns who opened our eyes an instant ago and are already trying to describe the whole room. We are still learning the grammar of light itself, still feeling along walls that may or may not be walls, still arguing about whether the emptiness around us is a local accident or a fracture in the foundation of physics. There's no shame in that. There's something almost unbearable about it, but no shame. We are children, and the thing we're trying to read is older and vaster and stranger than anything a child was ever asked to understand. Which brings me to the one thing in all of this that hasn't cracked. The one fact that stays standing after every certainty has been pulled out from under us. Anything looked at all. On one small, wet, rocky planet, orbiting an ordinary star, near the centre of a thin place in space nobody warned us about, matter arranged itself into something that could wonder. Something that could build a telescope, point it at the emptiness and say, there is something to measure. There is something wrong here. A mind trapped in a room still draws the room's shape, even when it can't step outside to check. And that act, that stubborn, doomed, magnificent act of measuring a cosmos we may be forever stuck inside, is the strangest and most luminous thing the universe has yet produced. Fear and knowledge, it turns out, are not opposites. They're the same thing seen from two sides. The dread you felt tonight and the awe underneath it are not in conflict. They're the same recognition that reality is larger and colder and more fractured than we were told, arriving in your chest as a chill and in your mind as a light. So we end back where we started, standing on ground that never was as solid as it felt, inside an emptiness we never chose, reading a universe that keeps refusing to agree with itself. And the question that no new telescope, no future survey, no cleaner data will ever fully close is this one. If the cosmos really is stranger and lonelier and more broken than we knew, does that make the fact that we know it more terrifying or more beautiful? I don't think you have to choose. I think the horror and the wonder are the same held breath. If tonight moved you, leave a like, subscribe so you hear when the next set of maps forces the fork closed, and tell me one thing in the comments. If the emptiness around us could answer, what would you ask it?